To tackle with embedded software, cross-compilation, low memory footprint, we have to generate C code or embedded C++. We have to develop real-time software, so we have to provide the schedulability analysis of our software. And we cannot use dynamic task creation or memory allocation. We have to build a deterministic software. So all our work is can be resumed in this diagram. So sometimes we have focused in the design and implementation, and sometimes we have also developed tools for handle the user requirements, the technical specification, and the functional validation, and the non-functional property analysis. So I'm going to start with the first approach that was the development of the Nanosat on-board software, where we design the software using room modeling, real-time object-oriented modeling with our tool, and we generate the code, C++ code, and we also know room is antecessor of the UML2 with clear concepts of components and message passing for the communication of the components. Each component has a queue of message, and the component works as a machine that processes messages. So each message has to be complete his process. After that, we can process the next message. So it's a machine that you can analyze. This is good for us. The behavior of the matching of this matching is defined by hierarchical state matching behavior, and we can program periodic events. But also we had in our environment and in our systems the necessity to handle with bursty events. So we extend the model to handle with this problem. The events are bounded, but they are not periodic. We have bursts of events. Wow. So we model this using a specific port to handle with interrupts. And we also extend the model to use always data pools to handle the data that are attached to the messages. So we don't use alloc, malloc, or anything like this. So we can have a deterministic behavior of our software. So we have some key aspects for build the delivery that we have to get. The mass model, the schedulability analysis over system. So we could, in this mission, provide this schedulability analysis. So we were very happy because this is one of the most difficult aspects of our task as a software designer. Well, we use also the same tool and the same techniques in Nanosat 1B, and also, well, I put this publication here, and also in the EPD software of Solar Orbiter. So after that, we try to cover other aspects of the software development as proof of concept. We didn't to build a professional tool, but we wanted to prove that we can do the things in other way. And we try to cover these other activities: the user requirement definition, technical specification, and functional validation, and the verification of the requirements for the validation reports. So we build an environment where we substitute the documents with models, and we use the this environment was built with EMF, so we can like a system powerful, and we can have a textual editor to build the models of the software system specification, software requirement specification. Well, we can import the TMTC, the telemetry and the telecommand from the database. So we can define the procedures, the software validation procedures, also in a textual language. And after that, we can generate the procedures that our tool, the ground support equipment with the ground support software, will run to cover the requirements. So after that, we can obtain a report that we can use to annotate our models and to build the software verification report. So the proof of concept try to substitute the generation of the documents by the construction of the models using also the textual editors. So we could get automatically the test that we have to generate to cover all the requirements. And well, we have this publication, this paper that explains this. And after this approach, we could cover the activities of user requirement definition, technical specification, functional validation, and the verification of the system level requirements. And we use also model to test transformation to obtain the documents. Well, thanks. Yes. Well,
sí. Es aquí, ¿no? Para pasar. Well, para abajo. Now I'm also continuing with the presentation. I'm going to talk about two other. Well, one of the aspects that Óscar mentioned, that was the how do we tackle with the problem of performing the non-functional property analysis, and also to deal with the problems related to managing the different software versions and the different deployments and the different deployment platforms that we use during the project. So basically, to explain the main problem, the idea is that when you develop software for onboard satellite systems, basically there are challenges that are specific of this domain and also in general of the embedded system development domain, which is that hardware and software are usually developed in parallel. So basically, during the whole development process, there are different hardware models that are used, starting from simulator engineering models until you reach the final flight model, which is basically the hardware that is going to go to space. So there is some variability between the different platforms that are used, and in order to manage that and to manage the configuration of the different software packages that form the process, we developed a framework that helped us, on one hand, to handle the configuration of the deployment of the application using models of the software packages. And we also, this framework also allowed us to integrate the existing tools that we used in the previous projects for developing the software, this headroom modeling and code generation tool, with analysis tools that allowed us to perform the schedulability analysis of our applications. So this is basically the scheme and structure of the software for the instrument control unit of the energetic particle detector instrument that Óscar mentioned about. It was on board the Solar Orbiter mission. So basically, we have here some packages, a service layer with some services on top of the real-time operating system, and on top of this service layer there was the main application code that was generated, partially generated with this code generation tool that mentioned. So everything, every part of this layer structure was modeled as a collection of software packages that were managed using this framework that we developed for this application. And the framework also allowed us to integrate our component model developing application with RapidTime, which is a tool that allowed us to extract the timing information, the real-time behavioral information of our application, to measure the time spent on each section of our code, and the real-time restrictions imposed by the requirements of our application to obtain automatically the input models for the mass tool that allows us to obtain finally the schedulability analysis of our application. So everything, this framework was also developed using EMF, Eclipse Modeling Framework, and all its environment, and well, it allowed us to successfully develop this workflow, this process for the project. And finally, I'm going to talk about one of our current research lines, which is a domain-specific programming language called Termina that we are developing jointly with researchers from the INTA Software Institute. And the main idea is that this language is specifically designed to develop embedded real-time critical reactive systems. So the idea is that this language uses abstractions that are really close to the domain, to the application domain, and we, from the definition of the software, we are currently finishing the implementation of a transpiler that generates MIS-RASI compatible code from the modules implemented in Termina. This generated code is executed on top of a runtime environment that basically acts as an abstraction layer for the underlying real-time operating system. So basically, this will allow us to use the code that is generated, use a single transpiler to generate the code, and then the code can be used on top of different operating system by only implementing this layer. We have currently implemented the layer for RTMs. So this language we built this language using some design principles. Basically, that we wanted it to be easy of learning and easy to use it. So basically, it follows an imperative programming paradigm with a syntax that is very close to that of C and Rust to facilitate its adoption. It incorporates, as I said, elements from the domain. So basically, We have on the language, at the language level, we have event emitters, we have tasks, we have event handlers, and the existence of this element at this language level will allow us to enhance the capabilities of performing a later analysis and verification on the generated code. Another key aspect of the language is that it follows, it's a reactive, it's a language designed for reactive systems. So basically, the way to program these systems is that you have to develop pieces of software that are executed in response to events. So these actions that are executed must always terminate. So basically, the language enforces that all the functions that you code are terminating. There cannot be infinite loops on the code that you build. Also, it enforces separation of concerns and ways to control the access of hardware, so that it also, by construction, guarantees that there are no race conditions and there are no deadlocks and there are no certain runtime errors, such as null-pointed references or memory leaks. And in regarding to memory also, it uses a deterministic dynamic memory management based on pools. So there is no heap, because heap is basically forbidden in this kind of environment. So this deterministic dynamic memory management also allow us to guarantee these properties. I don't know. I still have 2 minutes. So at this point, we are, as I said, we are finishing developing the transpiler to generate. We are almost finished, and we can so that we can generate the C code from Termina modules. We are also performing a transformation, let's say, as a transformation between that will allow us to obtain schedulability analysis model directly from the Termina models. So the idea is that we don't use as other approaches a high level specification model and then generate a skeleton of the application and then allow the programmer to build build pieces of code that may corrupt the complete analysis. So basically, the idea is that the analysis is built bottom up. So it's built from the directly. The schedulability analysis models can be built directly from the code. And the idea also this language can be used directly. I mean, it can be programmed directly. We're also developing a Visual Studio Code plugin so that it can be, so that it has some sort of these nice features that these plugins provide. It can be used to manually develop application, but it can also be used as a pivot language so that you can use you can define some higher level declarative models of your application and generate code to this, generate Termina code from these higher level models. And the Termina code guarantees by construction certain properties that cannot be guaranteed if you use a general purpose programming language. So that's the main idea. To validate the capabilities of the language, we are currently re-implemented a simplified version of the application software of the instrument control unit. This is the qualification model of the unit, and well, this is the component architecture of the software. And we once we finish this first software, well, the idea is that in the future, what we plan to do with the language is update it to support features such as generic programming and support for symmetric multiprocessing systems in the language. Use static analysis techniques such as abstract interpretation to guarantee the absence of runtime errors, such as indexing out of bounds, array indexing out of bounds. And we also are looking for collaboration opportunities. So if you want, you can reach us, and we will be glad to talk about this and all of our research line that we're currently involved with. And I think I'm mostly in time.
Yeah.
Thanks.
Thank you. Yes, thank you for a very nice talk. Are there questions?
How do you verify temporal constraints? Are you using some kind of logic reasoner or simulation and testing?
We use the mass model, and mass provide the schedularity analysis. So the problem is to measure the worst case execution time of the functions. But if you have the mass model, mass provide you if the system is or the system deadlines are validated or not.
Yes. The idea is that you need to.
Yeah. Our goal was we need to develop something that fulfill the requirements to build a mass model. So we start with a room model, and after that we modify the model to add the elements that guarantee that the mass model could be built. And that was all first from the room tool, and now with Terminal, because the schedularity analysis is difficult.
Yes.
It's not easy, and for us was an achievement that we wanted to.
Not all the applications that you can build using a general purpose programming language can be later analyzed the real-time behavior. So basically you need to build your application in a certain way so that you can obtain this model, and obtaining this model from inspection of the code is not easy. It's not easy at all.
Every event has its transaction in a match model, in a master model. So the transaction are defined, and after that you have to use the tool.
Okay, termination is obviously very important in the terminal language. How did you ensure the one completion while allowing recursion and function calling?
We don't allow recursion.
Okay.
Yeah, this was a quick question.
Yes.
And the loops are
And the loops are all bounded. They're all 4 loops.
You can
end the loop before it completes the.
You cannot use a variable to bound the loops.
You have to have some checks that indirect recursion is not possible.
That's it.
We have a question in proxy hands. Why using Misra C instead of Sparkada?
Well, yeah. Basically, because we had already our main experience with we have not used Ada for our projects. So basically, it was just easier for us. Yes, easier for us to generate. But we believe that you could generate a Sparkada from the code and benefit from all the tool work that is built on top of that Ada core has built on top of the environment, on top of the language.
Yeah, my question is, I like the approach, so don't get me wrong, but I've seen this approach being taken by others as well. And if I look at, for example, what Taste has, 95% of the functionality that you're aiming for is already present there.
Yeah.
So what was your decision to go for another approach and not take something which is already there? And I mean, Taste is not the only one. I know at least of 2 or 3 likewise implementations that do exactly the same.
The question is about Termina, or
Well,
because
the approach in German, yeah.
The approach was in the 2001. So
Taste is 15 years old.
and this is 25 years old. So we started a long time before. I had the papers there, and well, after that we had code generator that worked fine. So, and we could debug the code because it's very readable. So after that, we don't have a lot of people in our team. So maybe if we will a lot of people, we can test other tools. I every year have a presentation of tests in our because we are from the university, and I see that the learning curve is not short. So I'm afraid that if I start with this in the middle of a project, maybe I will be in a hole that I cannot afford. So
yeah, but now the problem is that you have to build up your own tool chain, which also is infinitely bounded in terms of resources.
Yes.
It's a trade-off, right?
Yeah.
Exactly.
Yes.
So I mean, the general point I'm trying to make is we need to join forces much more than we're doing right now. So I'm not complaining that your approach is negative. No. I do have a technical question though, if I may, is that time?
One quick question.
So, is your intent to do qualification at the level of the Turma modules, or are you still qualifying the C code that actually is the output of it in terms of qualification needs for ECSS?
That's a very
C code.
A very nice question.
You qualify the terminal.
Yes. The idea in our ideal world with infinite resources, we will try to build this transpiler using some sort of concert.
Yeah.
So the idea is that somewhere in the future we could perform this translation so that we can guarantee that
because there have been also approaches to qualify code generators, for example, from Seville directly to this kind of environment as well. Same approach.
Yeah.
Yeah.
So,
Coffee break time.
Coffee break time, exactly.
That's also for the next questions, if there are still any, so I hope it's okay to postpone them. Let's thank the speakers again.